All right, good morning, everybody. We are at the end of week 2 now. This is geometry still. Tuesday, we talked mostly about slope and sort of got into the beginning of equations. You know, the two primary types of equations that we work with. Actually, one primary is slope-intercept. That's the old y equals mx plus b format. And then standard form. They're interchangeable. We can take the standard form and convert it to slope-intercept if we solve for y. The next page after that, though, has this handwritten note at the top that says homework 6. Do not have this assigned as homework, but it is something that we probably need to spend a little bit of time on before we start looking at the parallel lines and transversals. So before we came on, I asked about if anybody remembered how to do this, and had an idea, but it wasn't quite right. So what I want to do is go ahead and start with this first problem. There's a couple different ways you can solve these. Does anybody remember point slope form? Point slope is actually probably my least favorite form of equation. So I'm not going to spend any time on that, but with the information that they're giving us on these problems, we can use slope-intercept to solve and to find an equation. So our slope-intercept form, y equals mx plus b. Audrey just told me point slope form, which is absolutely correct. This first problem actually is a perfect one for point slope form. Let's see. There is point slope form. You got the equation already?
Yeah, for number 1.
Wow, what'd you get?
Y equals negative 6x plus 4.
Okay, I'm going to write that down. Okay, that's Audrey's here in class with me again today. She's got the first problem solved. So we'll check it here because I don't know if that's correct or not. The one thing that I will say is absolutely correct is the positioning of this negative 6. If you notice in both of these equation forms, m is present. M is always going to be our slope. So if we're using slope-intercept, what we need is m and b. We need that y-intercept to be able to write an equation. So they give us this problem that says our slope is negative 6, and we have a point that the line goes through. It's not the y-intercept, so we have to find the y-intercept, but we can use the values from this point. It's on the line, so we can start doing some substitution. And if we use slope-intercept to do that, it'll help us find b. The y value from the point is negative 2. Our slope is negative 6. X is 1 from the point plus b. Okay. That's going to allow us to find the y-intercept. Now it's just equation solving because it's a one variable equation, right? So negative 6 times 1 is negative 6. In order to cancel that, we've got to add 6 to both sides to get the B by itself. So 4 equals B. And there is the y-intercept that Audrey told us. That's exactly the same as what I get. So all you have to do then, you're given the slope, and now we've just figured out what B is. You plug it in into a new equation that's specific to that line. This is straight out of week 4 of Algebra 1A. So it might have been a while since you guys have done these kind of problems. Does that ring a bell with anybody? Now, did you use point slope, Audrey?
Yeah.
Okay. Point slope is another one that is very helpful in the right situation, because what we have to do allows us to find the equation directly. There's a couple of things I don't like about point slope. I'll show you those here in a minute. I think I have these backwards. Yeah, I do. Should be y minus y1, because the y1 signifies the actual point that's involved. We're going to do the same thing as we did before with the substitution from the information that they gave us. I need to erase this and start over again with this, because I had the numbering, the lettering in the wrong place. Because the x and the y that are in point slope that don't have a number with them, those are the permanent parts of the equation. The x1, y1 are from a point that's on the line. So if you know a point and you know the slope, this is a good formula to use to calculate your new slope-intercept equation. And all of it essentially means you solve for y. The thing I don't like about point slope is these minus signs in here that causes our original values to change signs. Because when I start plugging these in here, I got y minus the y value. Well, the original y value from the point is -2. So now that becomes plus a +2. My slope doesn't change. It's still -6. Now I'm subtracting the x value from the point, which is a +1. So that means it changes to -1. So you still got an equation that's easily solvable, but it's more steps. It's a little bit more work. Now you got distributive property. You got to do that. Y plus 2. On the right-hand side, -6 times x is -6x. -6 times -1 is +6. All I got to do to get y by itself, because that gets us, it's almost in slope-intercept form now. And we're going to end up with exactly the same equation as we did doing it the other way, using slope-intercept. Questions, anybody so far? Now, if I go back to the handout, those first two problems are exactly the same, just like the one I just did. What's different about number 3 and 4? What do you also? Go ahead, I'm sorry.
You're not given the slope.
Correct. There's not, the slope is not given, but can we find the slope? Audrey says we can, and I would agree with her. We use the slope formula. That's what we were doing Tuesday when we were looking at the whether or not lines are parallel based on their slopes. Remember, y2 minus y1 over x2 minus x1. So we're going to have to use both of these, the ordered pair values from both points in order to do that, to find the slope. But after you've done that, all you have to, you can pick one of the points to either do what I just did with slope-intercept or with point slope form. So that's the only difference with this sort of a problem. -5, 5, and 5, -3. So part of what I'm trying to do here is reinforce some of these equations. So that what example on the left is using slope-intercept. The one in the middle is using point slope form. And I don't want anybody to forget the slope formula. Y2 minus Y1. Remember, this is just a comparison of the X values and the Y values. Rise over run. The Y values are the rise. X values are the run, the left to right. Okay, make that look like a fraction. So if I pick this particular problem, I've got -5, 5 is 1 point. The other point is 5, -3. Just plug them into the slope formula to find the slope. And then after that, I can choose one of these points and do either of these other techniques to find the equation. The instructions say find the equation in slope-intercept form. So ultimately, I need to end up in y equals mx plus b form. So this is my first point, -5, 5. 5, -3 is my second point. So I'm going to start with that one, 3 minus 5. And that's going to be over 5 minus -5. Don't forget a sign here.
Wouldn't that be -3?
It is -3. Thank you. I didn't do that on purpose, but good catch, Jonathan. Here I'm saying don't forget the sign, and I did it. Yeah, boy. Good job. So if I go ahead and complete this, I end up with -8. This becomes keep, change, change. So on the bottom, then I got 10. And that's reducible. They're both even numbers. So my slope is 4/5 now. Don't really like working with fractional slopes. So which one of these terms do we want to work with? I am thinking about using slope-intercept form, so I know that my slope number is going to be multiplied against x. So I'm going to pick this second one. Doesn't matter, but at least there's a 5 in the x position, because that will help me with cancellation. Maybe that doesn't make sense right now, but again, using slope-intercept, y equals mx plus b. What's the y value? -3. I got it right this time. Equals my slope, -4/5 times x, which is 5. So my 5s are going to cancel. right? I can't quite make that look like I want to, but that's close enough. -4/5 times 5. Does it make sense when I say that it's going to cancel? Let me write it more upright. Times 5. How do we get rid of fractions?
Be 1/5, right?
5/1.
5/1.
Yeah, 1/5 is 1 being divided by 5. That's not what we got. We got 5 as a whole number. So it's 5/1. 5 divided by 1. We can put any whole number over 1 and it doesn't change the number. So now I got a 5 in the denominator, a 5 in the numerator. If I want to get rid of a fraction, I use the denominator number and they will cancel. So after that, I got -3 equals -4 plus b. Add 4 to both sides. So now I know that 1 equals b. Okay, so my equation that tells me what the line is that goes through those 2 points, my actual equation, I'm running out of room on that part of the page, y equals -4/5 x plus 1. Questions? Anybody? So if you want to take some of these and practice with them, there's also some really good videos on khanacademy.org that go through this kind of thing, how to write these slope-intercept equations. What they're expecting you to do with the rest of these problems is to remember 2 things. You've got to have the slope and you've got to have the y-intercept to write slope-intercept equations. That's why it's called that. That's why that form exists. Where you get the slope and how you get the y-intercept is pretty much up to you. Now, if you look at these first 5, 6, and 7, what's the slope going to be of our parallel of the line that goes through these other points? Because all 6 of these problems here are talking about 2 lines. Our second line is going to go through a point that they give us that's parallel to the first line. 5, 6, and 7 are all parallel. So what's the slope going to be for our second line? Yeah, keep going.
The same, 9/2.
Slope is going to be the same for parallel lines. So we're going to borrow the slope out of these existing equations. 9/2 in number 5, -4 in 6, -8/5 in number 7. Because remember, we just did a bunch of exercises with parallel and perpendicular. We went through those rules. Parallel lines have the same slope. So I got a second line, it's got to have the same slope or it's not parallel. So that's why I can take that slope in the existing equation and use it to help me write this equation for the second line that goes through that other point. Because then all I'm doing is setting up the y equals mx plus b calculation. Y is -4 equals 9/2 times -2 plus b. Now I can find another y-intercept. Because when you have parallel lines, the only thing that's different in the equations is going to be the y-intercept. So that's why you have to go through that process to find the y-intercept for that second line. the last three problems here, 8, 9, and 10, are asking you to remember the rule for perpendicular. Anybody other than Audrey remember? We just did this on Tuesday. Hopefully you haven't forgotten it already.
Wait, which one?
Perpendicular, what's the rule for perpendicular line slopes? You know this one too? Okay, well,
You flip it.
flip it over. So you got the reciprocal
and you
and change the sign, right? Remember the phrase negative reciprocal. Opposite sign and reciprocal. So for number 8, the slope that we're going to need for our second line is going to be 2/5. Because now we're applying the rule. That all 6 of these problems are about applying those rules to help us write an equation for a second line. So be sure that you got those rules clearly in your notes from Tuesday. They would have gone right here, 2 pages previous. So questions, anybody? I'm not going to do the calculations on those because it's the same process. It's the only difference is where you get the slope from. So you need M and you need B to write slope-intercept equations. Okay, now we're going to get into some other applications, some other situations that involve the concept of things being parallel. I don't know if any of you are into science fiction. There's a whole genre of science fiction, and some scientists even believe that that there are other universes, parallel universes to ours. You guys ever hear that? Anybody ever used to read Justice League of America comic books? They had their counterparts. Justice Society of America was in a parallel Earth. So it's an interesting concept that things could coexist. And there's some laws in physics that would allow you to think that that's possible in quantum physics. Thankfully, we're not dealing with that. It's fun to read. It's fun to think about. All we got to worry about, though, are parallel lines and parallel planes. Parallel lines are lines that do not cross. Under the second bullet point, it says there's a blank. Something are used to indicate the lines are parallel. This is another situation where you're going to have to learn some symbolism. If you look at these 2 lines here, line AB and line CD, you know these are lines because you have arrowheads at both ends, right? They're not segments. They don't stop at A and B. They go through A and B. They go through C and D, and they go on forever. That's what those arrowheads at the end of each of those mean. Well, what about these arrowheads in the middle here? Probably haven't seen those before. Those arrowheads graphically and symbolic tell you that those lines are parallel. Most of the time, they're not going to, the word parallel is not going to be written there. Under symbolic notation, it looks like this example. Double arrowhead, line AB, parallel to line CD. And now on the first unit test, I saw a lot of people confusing what a line segment is, how it's symbolically represented and how a line is represented. So you got to get these clear, use these and understand these symbolic representations. This double line in between here, it looks like two L's together or two ones together. That's the geometry symbol for parallel. So this is a complete sentence here. Line AB is parallel to line CD, period. The blank up here, you should fill in with arrows. It's these arrows, not the ones on the end, the arrows that are in between. And you'll see why this is important when we start doing other things with these parallel lines, like cutting through them with other lines. Parallel planes, very similar. There's no points shown on either of these planes, but if you remember from the definitions, we can use this script or stylized capital letter, fancy J and the fancy K, to indicate those are planes J and K. Remember the dash lines, that's part of something that's not visible. You can't see through whatever's on top of it, so it's representing that's underneath still. They're trying to show three-dimensional concepts in 2 dimensions. Skew lines is the oddball. If you look at that rectangular prism there, that box, they've labeled every corner. It's got the dash lines here for the parts under the bottom and on the back that you can't see. The skew lines, this is a very important, there's always way more skew lines than are going to be parallel. You know, line TP is parallel to line UQ because they're on opposite sides of the same plane. But TP and UV are not parallel. Those are skew. They haven't even listed all the skew lines. They're not in the same plane and they never intersect. So they've given some examples here, but that's not all that there are. I just gave you one that's not even in the list. So skew, if you're in construction and you look at something and say it's skewed, it's not a good thing, because that means that it's not square. Something's wrong with it. It's out of balance, or not parallel, or not square. So the bottom of that page is just exercises to help you find more examples. So if we wanted to find segments parallel to AE, okay, HD is parallel. It's on that plane on the back. FB is parallel. This is the front plane. This one back here with EH, AD, that's sort of the end plane. It's pretty easy. Examples of parallel planes: the top and the bottom, the ends, the sides. And how do we identify planes? How many letters do we use? Guys need to know this because it's on the test. How many letters do we use to identify a plane?
Is it 4?
Nope, that's too many. 3. We only need 3. Think of a stool with 3 legs. 3 letters to identify a plane. Only 2 letters to identify a line. And some of you guys have been using 3 letters on some of these homework assignments to identify a line, and I'm counting that wrong, because that's not the process. That's not the tradition. 3 letters to me shows me that you think that's the plane, because that's the rule. That's the definition. Any questions so far? So here's a five-sided shape. It's a pentagon on each end. So they don't use dashed lines on this one, maybe because it would be even more confusing. But segments parallel to JK. Name all the segments parallel to JK. Anybody identify one?
Is it ML?
No, that's like the roof going up to the peak. That's not parallel to that flat bottom.
OP.
OP, there you go. That's right. JKOP is the bottom plane. That this kind of looks like a house to me. So that would be like the first floor. The only other line segment that's parallel is at the other end of that same plane, because the roof part of it, the top part of this shape, is on an angle. So segments parallel to NS, where's that? Okay. You got this one here, MR and JO, right? Top plane here, NMSR, side plane, NJOS. So this is where geometry can really get kind of tricky as you start to try to visualize some of these shapes. And I forgot to bring it in again today, but I've got some triangular stuff that I'm going to bring in and show. If you ever have trouble like with this first one here, this box shape, just grab a box of Kleenex or something like that and think about how those corners are. You know, the face that you see and the faces that you don't see, etc. There's plenty of examples that can match up with these kind of shapes if you need to practice. Now here's where we really get into what I think is a fun section of this unit with geometry. Talking about transversals and angle relationships. The next part of this talks about transversals going through parallel lines, and those situations have some very special meaning. But in all the rest of these cases here, angles formed by transversals are described in these four ways here. A transversal is simply a line that intersects two or more lines. So in this, at the top of the page here, the example is line T. That line goes through line L and line M. So the transversal is line T. So what they've done here is they brought the same example down here in this diagram and put it next to these definitions here. These four definitions: corresponding angles, alternate interior, alternate exterior, consecutive interior. Corresponding angles, same side of the transversal and in the same position. Well, what does that mean? Okay, here's our transversal. So if I'm looking for an angle that corresponds to angle 1, I need another angle that is on the left-hand side of that transversal and above the other line, right? Because angle 1 is above line L and left of the transversal. There's only one corresponding angle to angle 1, and that is angle 5. 1 and 5 are corresponding because they're in the same relative position in that diagram. Four and 8. Angles 4 and 8 are corresponding angles. Left side of the transversal below those respective lines. So it's the relative positioning that's important to identify, help you identify these corresponding angles. So there are a total of 4 pairs here. You can see they're looking for 4 examples here. All of these always come in pairs. Corresponding, alternate interior, alternate exterior, consecutive interior. It's always pairs of angles. There are 4 pairs of corresponding angles. I did all the ones on the left-hand side of the transversal. Can somebody give me one from the right-hand side? What angle corresponds with angle 2?
6.
Yep, there you go. To the right of the transversal, above the other line. Above L, above M. So that only leaves 3 and 7 as the last pair of corresponding angles. Okay, now these next two, alternate interior, alternate exterior. Well, the first question I get a lot of times is, what interior? This is not even a closed shape, right? It's not a box. It's not a triangle. It's just some lines. Well, this is, if you're so literal that you can't imagine that this area in here between L and M that is the interior of this diagram, this is going to be a hard one for you to understand then, because that's what they're talking about. So that means, conversely, that the area above L and the area below M, that's the exterior. And I know it's not a closed shape, but if you can imagine, these two lines here are sort of creating space. They're defining some space. Angles 3, 4, 5, and 6 are all in the interior. Angles 1, 2, 8, and 7 are in the exterior of the shapes that those lines L and M are defining. T is still your transversal. So alternate interior just means if you pick angle 4, I got to go, that's on the left side of the transversal. I need angle 6 to be the alternate interior angle. It can't be next to it. It says interior angles non-adjacent. So it's not the one next to it. You go across the transversal down to the other side. Kind of in an X shape, if you will. 4 and 6 are alternate interior. 3 and 5 are also alternate interior. You notice they're only giving you two blanks to fill in for those. Same thing holds true with alternate exterior. 1 and 7 and 2 and 8. It's a little bit larger X if you go across that transversal to the alternate side. The last of these definitions, consecutive interior angles. If you kind of just run if my mouse were your finger on a piece of paper and you're running your finger down this transversal, the ones that are consecutive are the ones next to the transversal inside the two lines. So 4 and 5 are consecutive interior. 3 and 6 are also consecutive interior. And the reason that those four definitions are important, you'll see that here in a minute when we start looking at parallel lines and transversals, because these relationships tell you something really, really important. It's going to allow you to solve for angle measurements. Think back to when we were talking about vertical angles, and I told you that if I knew one angle measurement, I could find all the rest. That when we get into transversals and parallel lines, it'll seem very similar to that. So I would encourage you to take a minute and get some of these examples written down in here, because you should make some notes so that you can come back and refer to this later, because these definitions are going to they're going to come up again throughout the rest of this term. So this isn't something that you can learn this week and forget. You're going to use this for the rest of this term in geometry. This, especially once we start thinking about shapes that have parallel sides or are being cut through by other lines or other shapes. It creates a lot of these relationships: corresponding angles, alternate interior, alternate exterior, consecutive interior. Those are special definitions that you got to pay attention to. Questions on any of that so far? Does anybody need more time to get some of these examples down, or did you get what you need? Okay. So at the bottom of this page, I'm going to skip the first example because it's exactly like the diagram. It's just rotated. The second example, though, might have you scratching your head a little bit, because now you got four lines and you're going, okay, well, which one of these is the transversal? Well, it depends. Remember, the definition of transversal is a line that cuts through two other lines, two or more other lines. Okay, so line A could be a transversal here for these 1, 2, 3, 4, 9, 10, 11, 12. Line B could be a transversal also for these 5, 6, 7, 8, 13, 14, 15, 16. This line on the angle up above here could be the transversal for these other two lines. And look at the numbering: 1, 2, 3, 4, 5, 6, 7, 8. Line D could be a transversal for the rest of those. Since we're talking about relationships spatially, which examples you're looking at are going to depend on those relationships, which is the transversal, which are the two lines that are cutting through. So angle 5 and angle 13. Angle 5 and angle 13, those are both on this transversal B. Those are corresponding. Right? Same side of the transversal. Same relative position to the lines that the transversal cuts through. Now, what about this example down here at the bottom? Angle 6 and angle 11. Here's angle 6. Here's angle 11 down here. What relationship, if any, are those two angles in? 6 and 11.
Are they alternate exterior angles?
Well, anybody disagree with Jonathan or have a different idea? The issue there, Jonathan, with that is they're not on the same transversal.
Oh,
So that they don't, there is no relationship between those two. And that's why I kind of scanned down through this list here to look for one of those examples, because all of these definitions here involve situations along the same transversal. You can't cross over to a different transversal. Relationships are not the same. 4 and 13, very similar. Example I down here, angle 4 and angle 13. 4 is on this transversal, or that one, depending on how you look at it. 13 is on this one or on that one, depending on how you look at it. So there's no relationship there either. So there's the two examples you see down here in the list. No relationship. All the others are in one of those other definitions. And the thing I'm going to try to emphasize here, if I can get this position right, name the, look under your examples here, right at the top, it says name the type of angle relationship. If no relationship, write none. So that right there in the instructions tells you that there's a possibility that some of these might not fit into any of those definitions. They might not have a relationship. So just because you see it, you know, you're shown something on a drawing, doesn't necessarily mean that it's going to fit any of the definitions. Questions, anybody? Okay, the next page is another one of these graphic organizers. Really would be a good idea. And if you have to come back and watch the video again later, get all of this in your notes. You can see down at the bottom there are non-examples. It's basically the two situations we were just looking at. And the key to all the rest of these definitions is this part up here. Name that transversal. Okay, so for angle 1 and angle 12, L is the transversal because that's the line that those two have in common. Angle 3 and angle 6, here they are. Those are both on transversal J. So remember me saying before, sometimes you have to sort of visually ignore some parts of drawings to understand what you're looking at. This is another good example of that. If I'm looking for 1 and 12, then I'm talking about these 8 relationships here. I don't even care about the stuff that's over there on line M. Because 1, 2, 3, 4, 9, 10, 11, 12, if I'm on this transversal, those are the only relationship angles that I care about. Same thing over here, 3 and 6. Those are all all of those 1, 2, 3, 4 up through 8, those are on line J. So I don't even care about what's down here on line K because they're not in a relationship. So you got to really concentrate on identifying the correct transversal first. This could be a good one to practice with if you wanted to do homework 7. It's not an assignment. I'm not assigning that because it's just more practice. If you can identify these relationships, you'll be fine. Now, the next page, you absolutely have to concentrate on getting this page into your memory somehow, because this is where those definitions are most useful. Because now, since we're talking about parallel lines and transversals, not only do we have these definitions that govern angle relationships, but those angle relationships are very specific in terms of congruency or being supplemental. One way to think about it is if you have, let's say in the room that you're in, the line where the wall and the floor come together and the line where the wall and the ceiling come together, those lines are parallel, right? So if you took a marker and you just struck a line across the wall, through the ceiling, down through the floor, you're going to create some of these relationships. If you look at the corresponding angles, they're going to be congruent. Alternate interior angles are congruent. Alternate exterior angles are congruent. We might even have vertical angles. We already know about vertical angles being congruent. Consecutive interior, for these new definitions, these 4 relationships, that's the only one that's different. That's the only one that's supplementary. It also reminds you below here that a linear pair is always supplementary. So what's a linear pair look like? Linear pair is 2 angles.
Is it 2 and 4?
What I'm drawing here on the whiteboard is a linear pair. 2 angles that create a straight line.
Oh,
So right here in this box, you've got 2 things that came from day 1 from our definitions. Vertical angles being congruent, linear pair angles being supplementary. Okay, now what did you ask me, Audrey? If you're talking about linear pair,
I thought I said 2 and 4.
that's vertical.
That's vertical, yeah.
If you look at these drawings here, and this is what I'm talking about with these examples.
Oh, wait.
If we know one of the angle measurements, we know all of them.
Yeah. So 1 and 2.
Those are linear pair. So if angle 1 is 65 degrees, how much is angle 3? 65. How much is angle 5? $65. How much is angle 7? Right. So because now we're talking about parallel lines, these are predictable and guaranteed numbers if you know one of the angle measurements. So since we know that this shape up here at the top, this 1-2 combination is a linear pair, now how much is angle 2? If angle 1 is 65 degrees, how much is angle 2? A little too high. Audrey said 125. That's a little bit too high. That gives you 190. 115. So 2 and 4, those are vertical angles. Those are also 115. 2 and 6 corresponding, those are 115. 8 is a vertical angle of 6. That's also 115. Example 2, just another of the same kind of thing. I know these are parallel again because these little arrowheads that are in the middle of the line somewhere. Angle 6 is 142. And usually for me, what I try to do the easy ones first. Don't worry about the relationships. And visually you can check yourself too, because if I'm told like this one that angle 6 is 142 degrees, automatically I know that angle 1 is 142 degrees because of the vertical pair. I don't need to know anything about corresponding or anything else. In fact, both of these first two problems I can really pretty much solve just knowing the definitions for vertical pair, vertical angles, and linear pair. Because look, 5 and 6 together makes a straight line. Okay, that's a linear pair. So 142 from 180 is 38. So angle 5 is 38. Now with the vertical angle, 1 and 6 being 142, I just figured out what 5 is. Now I also know what 2 is. It's also 38. They just try to keep making it more complicated. Remember at the beginning with the transversal definition, it said a line that cuts through 2 or more other lines. Well, our transversal is this horizontal line here. And these 3 lines going up and down, those are the parallel lines that we've got. All right, because they also have those little arrowheads on there. There's no words on this problem that tell you that that's parallel. You have to know the symbolism. So if angle 5 is 82 degrees, angle 8's 82, angle 6 is 82, 9's 82, 4's 82, 7's 82. The others, 11, let's see, 82 from 180, 98. All the rest of those are going to be 98 degrees. How many of you think that's right? Well, let's see. Yeah, there you go. 82 and 98 degrees. Questions on how I got any of those? All I'm doing is using the definitions.
Mr. J, can you go up a little bit so I can get that top part right there?
Right here?
No, the one above it.
The example, let's talk about example 2.
Yeah. Yeah. Thank you. All right, I'm good.
Thanks for speaking up. Now here's the one that's going to really get fun. Example 4. 4 and 5 look complicated. And this is another situation where you've got to think about what's the transversal. So the thing that I noticed first is that this line, the horizontal lines on example 4 are the ones that are parallel because they've got, again, a little arrowhead that's in the middle of the line that tells me those are the parallel lines. So these other 2 lines, those are just 2 separate transversals. So what do I have here? I've got angle 12 is 121. Angle 6 up here is 75. Give me a minute here. I'm going to copy this and put it on a Jamboard, and we'll try to run through all these. What am I going to do first? I'm going to label these darn things. Angle 12 is 121. Angle 6 is 75. So I'm going to do the easy ones first. How much is angle 11? Isn't that a linear pair? Everybody should be shaking their head. Yeah, it is. Because they create this straight line. So 180 minus 121, 120 would be 60. So angle 11 is 59. How much is angle 7? Well, vertical angle. Angle 7 is the same as angle 12, 121. 8 and 11, another vertical angle pair, also 121. Haven't done anything on any of the rest of these lines yet. Now, what's the next one I can do? I can figure out angle 4. 4 and 8. What's the relationship there? Four and 8 are alternate interior. I know because the definitions, that means that they're congruent. So I got angle 8 of 121. No, I don't. I got that wrong. I put the 121 in the wrong spot. That's not 121. You guys got to catch me on this here. 11 and 8 are the ones that are the same. It should have been 59. So that means angle 4 is 59 also. And you want to know how I really caught my mistake? Think about what an obtuse angle is supposed to look like. 12 and 7 are the obtuse angles. They're bigger than 90 degrees. They're opened up. 4 and 8 are not obtuse. Right? So can I do anything else with 1, 2, 3, or 5 right now? How much is angle 5? Four, 5, and 6. It's a straight angle. Creates that other line. Right? So 59 plus 75 is 134. 180 minus 134. 46. Okay. So now I figured out angle 5 is 46 degrees. So how much is angle 2? 46. Another vertical angle pair. 46. If only I could use this stylus the right way. So this is 46. Okay, what's angle 1?
75.
75. Very good. We're almost there. 3 and 4, another vertical angle pair. 3's got to be 59 also. All right. So how about these two, 6 and 10? Consecutive interior, which means they are supplementary. That's the oddball one. That's why I'm bringing it up. Supplementary. So 75 from 180 is 105. So that means angle 13 is 105. So 9 and 14 are the last ones. Those are 75 also. Six and 14 correspond. And the angles even kind of look alike. So all you did was work with what I was given, starting with some labeling, and then start to use those definitions. That's what pretty much all of this stuff in this part of the handout involves. So what I would encourage you to do is to do some of these other practice problems, because now they're going to start throwing some algebra in here. So like if you look at this first example, it says if line L is parallel to line M, find the missing value of each variable. Okay. So what's the relationship here between this 58 degrees and this 5x minus 2? Which one of those definitions fits that situation? You got only like 6 choices. Are they corresponding? Are they alternate interior? Well, they're not interior. To be alternate interior, they'd have to be in between the lines. So you can rule that out. They're not alternate exterior. They both have to be outside the lines. They're not considered. Huh?
You're not casting anything.
I'm not.
No.
Oh, why'd you let me go so long? You're probably the only one watching.
Probably.
Sad but true. Okay. Nope. Corresponding. Same side of the transversal, same relative position. Number 2, alternate exterior, outside the lines on the opposite sides of the same transversal. So those relationships are going to tell you how to come up with the equations. In this first one, it's 5x minus 2 equals 58. They're congruent, so you have to make them equal to each other. The second one, also congruent. 134 equals 16x plus 22. So those would be some good practice for you to work on between now and Tuesday. We still have a few more pages in this handout to get through. I don't want to rush through this because it's so important.
So for those, you just solve for x, right?
Yep.
So it's the same exact thing we were just talking about before class started.
Yeah. Yep. Exactly, Jonathan. You know, before we just had the definitions for like bisect and for supplementary. Now you've got the added, it's actually a benefit because now you're starting to see some things that you know are congruent just by their positioning. So that helps you with the equal signs for sure. Okay, guys, I'm gonna let everybody go. I got another class here in 5 minutes. So see everybody on Tuesday. Let me know if you got trouble and need some help. Okay.